Depending on the context, sometimes when we're thinking about quantifying our uncertainty with respect to some parameter, we might not want a confidence interval as much as we would want an upper bound or a lower bound on the value of the parameter. So instead of being able to say it's going to fall between these two values with some probability, we'd rather say, well, it's going to be less than this value with some probability, or it's going to be more than this value with some probability, right? And in trying to do this, what we're really asking for there is a one-sided confidence interval, right? Where we only want to provide either the upper bound or the lower bound, and on the other side of that, it could be, as high or as low as we would actually want. Right? And so one-sided confidence intervals can oftentimes be desirable. And depending on the situation, there might be reasons that you would want other asymmetric confidence intervals. Right? So for the mean, for instance, we might want a confidence interval that's not going to be symmetric about 0. And so the same types of procedures that are used to construct symmetric two-sided confidence intervals can be applied in order to generate one-sided or other asymmetric confidence intervals as well. So confidence intervals for any parameter can be asymmetric if that's desired. The symmetry in the confidence intervals and means is often going to be desirable, right? So this symmetry that is in the standard two-sided confidence interval is going to be a frequently desirable occurrence. However, it's not going to be the only possibility here. So to think about how we might generate an asymmetric or a one-sided confidence interval, it's worth thinking about the definition of a confidence interval. And so confidence intervals are always going to be defined based on containment probabilities. So specifically, a confidence interval is going to be given by two estimators, which we'll call L and U here. And they're defined such that the probability that the true value falls between L and U is going to be 1 minus alpha, right? To get a 1 minus alpha 100 times 1 minus alpha % confidence interval. Okay. So the estimators are random variables, and they're going to be dependent on the observed sample, right? We're sort of suppressing that notation there, but we're thinking about L and U as being random here. Now, any interval that holds this property is going to be considered a confidence interval, right? So any estimators L and U are going to be valid as long as they meet this desired property. And so they don't have to be symmetric, they don't have to be equal distance apart, they don't have to be anything too specific, as long as when you calculate out this probability statement, the probability statement holds, then it's going to be a valid confidence interval. Right? And so what this is going to do is it's going to open up many different variants of intervals for both means and proportions. Right? The standard intervals for means and the standard intervals for proportions are symmetric and two-sided, but there are going to be many other variants that are going to be opened up by using this definition and then just deciding that we want it to be one-sided or we want it to be asymmetrical. Okay? So let's think about a one-sided interval for the mean then. If we were drawing from a sample that's a normal population with a known variance, so starting from sort of the easiest set of assumptions that we can work with here, then the standard two-sided confidence interval is going to be given by x bar plus or minus the critical value times by sigma over the square root of n. Right? And so it gives us this interval of x bar minus the magnitude of it times by sigma over the square root of n, and then x bar plus the magnitude of the critical value times sigma over the square root of n. And what we're saying by this being a valid confidence interval, right, is that if we were to take the probability that we have, say, A less than or equal to theta less than or equal to B, right, where A is going to be this lower bound here, and B is going to be this upper bound here, right, then this is going to be equal to 1 minus alpha. That's what defines this to be a confidence interval, right? So that's why this is a valid two-sided confidence interval. And we say it's two-sided because the upper and lower bound are going to be both sort of equally well defined. But we could consider a one-sided interval, right? And the one-sided interval that we want to take a look at here is going to be given by negative infinity up to x bar plus z with alpha as the critical value times sigma over the square root of n. Okay, and so we can ask ourselves, well, what is the probability that mu falls into this interval here, right? And that's a worthwhile question to actually try to investigate here, because what we have going on here is it's a one-sided interval in the sense that there's only an upper bound, right? We don't actually have a lower bound because the lower bound is just taken to be negative infinity here, right? So there's no corresponding term on the lower side here. There's only an upper bound term. And so this is what we'll call a one-sided interval, but it's worth us figuring out, well, what is the probability that x bar or that mu actually falls into this interval here? And so we can investigate that. So a few things to point out is that because we're dealing with the normal situation here, right, what we have is that x bar is going to follow a normal distribution with a mean of mu and a variance of sigma squared divided by n, right? So that's the distribution that we know. And the interval that we're thinking about is this interval from negative infinity, and then we go to x bar plus z of alpha times by sigma over the square root of n. And what we want to know is, well, what's the probability that mu actually falls into this interval? And so we can write that out as the probability that negative infinity is less than or equal to mu, which is less than or equal to x bar plus z of alpha times sigma divided by the square root of n. Okay, and so that's the probability that we actually want to work out here. And so let's try to actually work this out. The first thing that I'll note is that this first term down here, right, this term is actually going to just always hold, right? Negative infinity is always going to be less than or equal to mu, right? Because mu is just some value that we're going to actually be working with, right? And so that's always going to hold. And so what we can do is we can actually rewrite this. So that's will hold forever. And so we can rewrite this as equaling the probability that mu is less than or equal to x bar plus z of alpha times sigma over the square root of n. Okay. Now, it's important for us to think about, well, what is the random term in this case? And the random term here is this x bar, right? The x bar is something that we know the distribution for. The distribution is going to be a normal distribution in this case, right? And so this is actually the only piece of randomness here. Everything else is just a fixed constant. And so because of that, what we can say is, well, this is going to be equal to, and rewrite this where we say mu, and then subtract off this term here, minus z alpha sigma over the square root of n is less than or equal to x bar. Okay, and so this right here is now a probability that we can actually think about. And it's going to be slightly easier for us to think about the complement probability, right? Because x bar we know is going to be a normally distributed random variable. And so instead of writing it like this, we can say, well, this is equal to 1 minus the probability, where we're just taking the complement here. Because we're doing 1 minus, we get to flip this sign around here, right? So that's going to be x bar being less than or equal to mu minus z alpha times sigma over the square root of n. Okay, and now we've worked through and we can start actually applying our normal probability rules, because at this point, we're asking a probability question about the sample mean where we know the sample mean is going to be normally distributed. Okay, and so what do we do from here? Well, we can actually come and write in that the probability that x bar is less than or equal to mu minus z alpha times sigma over the square root of n. Well, we can do our standardization procedure, right? So that's going to be equal to the probability of x bar minus its mean divided by sigma over the square root of n is less than or equal to, and then right here we take the same general term, right? So we're going to have mu minus z alpha times sigma over the square root of n minus mean divided by sigma over the square root of n. Okay, and we can come in and simplify these things in a little bit. This mu is going to cancel with that mu. The sigma over root n is going to cancel with that sigma of root over n. And so that's going to be the probability that, and we normally would call this term here equals z, right? So that's going to be the probability that z is less than or equal to negative z of alpha, right? And we're almost done here. Okay, so in terms of actually sort of trying to draw this to a conclusion, right, we have that the probability that z is less than or equal to negative z alpha, right? Because I can see that that's a little bit challenging to read in the red writing down here. So we'll write it out up here as well. Okay, and so then the only thing that we need to note here is what is this negative z alpha. And so the point is that this is going to be the negative version of the value here. But whenever we're taking alpha to be one of the smaller values, right, this is actually just going to be equals z alpha, right? So if we think about taking the critical values, if you take alpha to be, say, 0.025, right, then we know that that's going to be a negative 1.96, right, when we take z alpha. And so we just want the negative side of these things. And so in other words, this is going to be the probability that z is less than or equal to z alpha, which is phi of z alpha, which is exactly equal to alpha, right? And so we found that this probability is equal to alpha. And so then to conclude the proof here, we write that that is going to be 1 minus alpha. Okay, and so just to walk through what we've actually done, we started with this idea that the sample mean is normally distributed, and we have this interval, and we want to know, well, what's the probability that we're in the interval here? So then we say, okay, well, let's just write this out as a probability statement. We can drop this lower bound because that lower bound is not random at all. That's always going to be true. And so we're just looking at the upper bound. The upper bound is a probability based on x bar, right? So we can rewrite this expression using x bar by itself. We take this now as just a normal probability calculation, and so we've rewritten it using the complement probability. To solve for this one term, we can work through standardization, work out that it has to be equal to alpha, and so then on the whole, we have 1 minus alpha as the probability here. And so what that means is that this interval that we've started with, there's a probability of 1 minus alpha that the true parameter value falls into it. And as a result, this interval right here is a valid confidence interval. There's a probability of 1 minus alpha, and so then it's a 1 minus alpha times 100% confidence interval for the mean, right? Perfectly holds in the same way that the two-sided interval holds as well. Okay, so what's the probability that mu falls into that? Well, it's going to be 1 minus alpha. And so this interval can be seen then as giving an upper bound on the mean with some level of confidence, right? So instead of us thinking about, well, what's the lower and upper bound, we're really just saying, well, we can have the upper bound by itself. Okay. We could have also done the exact same procedure except taking just the lower bound, right? And so in this case, we'll take x bar minus z alpha times sigma over the square root of n. Now there's something that's worth pointing out here, and that's the key difference between our standard interval, the two-sided, and either of the one-sided, right? And of course, the first difference, the sort of most obvious, is that we're starting at, say, negative infinity, or we're going to positive infinity. But the other difference, and it's a little bit more subtle, is that we're taking the value z alpha rather than the value z alpha over 2, right? And so when we're doing a two-sided interval, we have to take that alpha and we're distributing it to both of the tails of the distribution, right? So we're going to put some of the alpha into the upper tail and some of the alpha into the lower tail, right? And so if we take our bell curve here and we think about what we're normally doing, with our regular, we're going to take alpha over 2 and alpha over 2. So in both of these cases, we're going to have sort of an alpha over 2 into both tails, right? But when we want just an upper or just a lower tail, that's not what we're going to do anymore. Instead, we're going to say, okay, well, actually, we only need to cut off at the upper bound. And so we're going to come and we're going to take all of the alpha and put it into one of the tails there, right? And so we're using different critical values here, but otherwise the procedure is going to correspond in almost exactly the same way. Okay. Now beyond this, we can sort of work on sort of more general one-sided intervals. And what we mean by this is that we don't have to derive them from the assumption of normality. In fact, if we had the use of the central limit theorem instead, then we could have taken the t-based intervals and used those in much the same way. And if you work through the exact same procedure that we were just working on before, then what you're going to find is that the intervals that plug in the t with the alpha as the critical value and use the sample standard deviation, they're going to provide valid one-sided intervals as well for the exact same argument that we just went through. Okay. The other thing is that if instead of means you were working with proportions, because proportions are based on the exact same idea as well, you can use these as a single-sided proportion interval as well, right? So the same procedure is going to apply whether we're talking about means in the normal case, whether we're talking about means where the variances are unknown, or whether we're talking about proportions. It's all going to follow the exact same type of procedure here. Okay, so all of these intervals are going to be useful if what we want is a one-sided bound. So we want to say that there's going to be less than some value with a certain probability, or that it's going to be above a value with some probability, right? Just a one-sided bound. If what we care about is really a one-sided problem, then these types of intervals are going to be quite useful for us. Now, in general, Z alpha is going to be less than Z alpha over 2 in terms of the magnitude of it, right? So really, if we were being sort of a little bit more cautious here, we would have been writing that this is going to be the magnitude of Z alpha is going to be less than or equal to the magnitude of Z alpha over 2. And we saw that before on the previous slide with thinking through what the differences was. But so what this means for us is that the upper or lower bounds are going to be closer to the mean in the two-sided intervals, right? And so in other words, if you're thinking about, well, we have one interval that's computed based on just the lower bound and then the upper bound, right? So this is interval number 1 here. And then in interval number 2, we go from negative infinity up to, say, u star here, right? Then if we think about this, u star is going to be less than u. Okay, and that's going to be because of the fact that Z alpha is less than Z alpha over 2. So in a way, this is going to give us a tighter upper bound. It's going to give us an upper bound that's even less. And the sacrifice that we pay is that negative infinity is going to be a lot lower than L, right? And so we trade and we say we don't care about what the lower side is going on, but we want to have sort of the best upper bound that we can have, and we can get a closer upper bound if we do the one-sided interval here, right? So that's sort of the benefit to doing the one-sided interval. The other way that you could think about this is that if you wanted to use the same bound, so if you want to take the same interval, right, and you take the value at Z alpha over 2, then you can actually half the level of significance, right? So instead of having this be an alpha, a 1 minus alpha confidence interval, you could have this be a 1 minus alpha over 2 confidence interval. And in that case, you're going to be more confident using the same upper bound, right? But again, you're sacrificing the lower bound here. Now, because you're sacrificing the lower bound, these intervals are always going to be wider than the two-sided intervals, right? So if you go from negative infinity up to the upper bound, even though that upper bound is lower, negative infinity is a lot less than whatever lower bound you've calculated, right? And so they're going to be wider than the two-sided interval, but it gives you a better bound on either the upper or the lower end, depending on whether you're looking at the lower or the upper confidence interval here. So we can take a look at an example to make sure that calculating these is going to make some sense. So we have a pharmaceutical company here. They've developed a medication to lower the systolic blood pressure, right? A clinical trial is conducted with a sample of 100 patients. The average blood pressure reduction is 15 milligrams of mercury, millimeters of mercury, with a standard deviation of 5. Okay. And so what's a lower bound on the average blood pressure reduction at a 95% confidence interval? And so the idea here, right, is that they want to know, okay, we've estimated that the effect is going to have an average of 15 in terms of the reduction, right? But we know that that effect might not be the actual reduction. And so if we wanted to report, say, the 95% with 95% confidence, what is the lowest possible effect that we're estimating, then that's sort of a worst case scenario in this case, right? Because if you want to see, well, how much is it going to reduce your blood pressure by? Well, we want sort of a lower bound on that reduction, right? And so this makes sense to take a one-sided interval because, of course, if the reduction is even higher than this, then that's going to typically be more good, right? That's going to be preferable. And so instead of thinking about, well, what's happening if it's higher, that's just a positive for us. Let's think about figuring out, well, what's the best lower bound that we can come up with? And so to do this, right, we take in our information. N is going to be 100. X bar is 15. Sigma or S is going to be 5 in this case. Okay. And so we want 95%. And so we can work through and figure out how exactly to solve for this. So because it's a large sample, we can proceed with the t-based intervals. We have x bar is 15 and s is 5, right? N is 100. Alpha in this case is 1 minus 0.95, so it gives us alpha of 0.05. And remember, the critical value in this case is going to be an alpha critical value. We don't need to divide by 2. And so we want the t critical value with n minus 1 degrees of freedom, so t99, but at the 0.05, which is what our alpha was actually found to be. And this is negative 1.66, okay? Now in R, we can find this using the qt function, where in the qt function, we first pass in alpha, and then we pass in the number of degrees of freedom. And so that's going to be alpha is 0.05, number of degrees of freedom is 99. This is going to give us that negative 1.66. And so with all of this here, we can actually work out the lower one-sided interval here, okay? And so we want the lower bound on this, so we take x bar minus our critical value times s over the root n, and it's going to go up to infinity. So plugging in our values, 15, 1.66, 5 over the square root of 100, okay? And that's going to give us a lower bound of 14.17. And so the idea here is that from the information, we can say that we're 95% confident that the effect is at least 14.17 or higher, right? In terms of the reduction. You're going to get at least a 14.17 millimeters of mercury reduction. Maybe a larger reduction. It's going to be somewhere between there and infinity. We could have found a confidence interval for the effect, the reduction here, but in this case, all we want to report is what is the minimum that we're expecting this effect to actually be. So what's actually going on with these, right? It's sort of nicely summarized in the different graphics that we have here, right? And the idea is, where are we actually putting this probability, okay? And so in all of these cases, we know that we want 1 minus alpha to be covered by this probability. And so if you want a lower confidence interval, then the idea is that we're going to take all of the alpha that we're not including, and we're going to put it in the lower tail, right? So it's all going to go there. If you want an upper one-sided interval, then we're going to take the full set of alpha and we're going to plug it in over here. And if you want the two-sided interval, you're going to split the alpha between the tails, right? So you're going to put alpha over 2 and alpha over 2, and then combined between these two areas, you're going to have the alpha, right? And so in each case, we're leaving out alpha of the weight of the probability, and it's just a matter of, do we cut it off on one side, on the other side, or on both sides? And so the lower one-sided gives us just the lower bound, and that lower bound is going to ultimately be specified at the Z alpha critical value, or based on the Z alpha critical value. The two-sided interval is going to be based on the Z alpha over 2, and then the Z1 minus alpha over 2. And the upper is going to be based on the Z1 minus alpha. And so we can see, sort of looking at these graphics, the point is that this Z alpha, right, if we were to move the Z alpha onto this plot over here, it's going to be somewhere like there, right? And if we were going to move the Z1 minus alpha, it's going to be somewhere like here, right? And so if we think about this as sort of being the estimated mean, right, then what we're going to have is, this is the estimated mean, right? We have our Z1 or alpha there, our Z1 minus alpha is here, right? In both cases, the lower bound or the upper bound are going to be closer to the mean. But what we're sacrificing is, if we think about this one-sided upper tail, right, we have no idea what the lower bound is going to be, right? It could just go on forever in this way. There's sort of no actual lower bound to it. Whereas in the two-sided interval, we're saying, okay, well, we're not going to get the best upper or the lower bound, but we're going to get bounds on both sides here. Okay, and so that's sort of the distinction that we're making here. So the lower one-sided intervals provide only a lower bound, the upper one-sided intervals provide only the upper bound, the two-sided intervals provide both, but they require them at sort of more extreme values. Okay, all of these intervals, though, have 1 minus alpha under the curve. The shaded area in each one of these intervals is going to be exactly 1 minus alpha, and it's just our choice as to how we distribute that 1 minus alpha under the curve here. We can also think about taking sort of more general intervals, right? So beyond one-sided or two-sided intervals, we can just form a general interval. And the idea is that as long as we're picking a lower bound and an upper bound such that that 1 minus alpha is actually true, then it's a valid confidence interval. And so in particular, if we're thinking about our normal values, then as long as we're taking critical values of ZB and ZA such that this difference is going to be 1 minus alpha, that's going to work, right? And so if we think about what's actually going on here, right, with our bell curve plot drawn out, right, the idea is that we're going to want to pick a critical value, which I'll call ZA, somewhere down here, and we're going to pick another critical value, which I'll call ZB, right here. And if we think about the probability that we're falling between them, right? It's going to be this whole area here. And this probability we can express as phi of ZB minus phi of ZA. Okay. And as long as this is equal to 1 minus alpha, this is a valid confidence interval. Okay. And so for us, what we can actually work out is because phi of ZB is going to give us B, and because phi of ZA is going to give us A, right? Then what we need is B minus A equals 1 minus alpha. And as long as B minus A is equal to 1 minus alpha, then that's going to hold perfectly fine, right? So this occurs as long as B minus A is equal to 1 minus alpha. And we can think about the values that we would normally pick here, right? So the normal values that we're going to take is we're going to take B is equal to, say, alpha over 2, or 1 minus alpha over 2, and A is equal to alpha over 2, right? And so then if we take B minus A, we get 1 minus alpha over 2 minus alpha over 2, which is 1 minus alpha, right? And so it holds for the regular intervals as well, but it's going to hold for any B minus A, or it's going to work for any B minus A in which that property holds, okay? So if we take the interval here, then that's going to be valid as long as B minus A is 1 minus alpha. Now the standard intervals, as we were just mentioning, take B is equal to 1 minus alpha over 2, A is equal to alpha over 2, so that we get the results, right? And then that's going to be plugged in as A and B in this expression, right? So if we plug in alpha over 2 and 1 minus alpha over 2, then this is our standard two-sided interval here. But again, it will work even if that's not symmetric. If we wanted to take a one-sided interval, right, we could take B is equal to 1 and A is equal to alpha, and that's going to give us, taking B equals 1, this value is then going to become infinity over here, okay? Because in order for it to be less than or equal to 1, then we would need it to be infinite. Alternatively, we can take B as 1 minus alpha and A is equal to 0, and if we take A is equal to 0, then this whole value down here is going to be negative infinity. Okay, and so in both of these cases, the one-sided intervals have exactly the same result as well. Okay. Now, it would be equally valid to take something like B is equal to 1 minus alpha over 10 and A is 9 alpha over 10, right? And if we think about why that's going to be the case, right? If we take B minus A, that's going to be 1 minus alpha over 10 minus 9 alpha over 10. That's going to give us 1 minus alpha, okay? And so while it'd be totally random for us to take 1 minus alpha over 10 and 9 alpha over 10, there's actually nothing stopping us from the definition of a confidence interval. There's probably no reason to do this, but it's still going to give you a valid confidence interval, okay? And the reason that there's really no reason to do this is because the symmetric interval is always going to be our most narrow interval, right? And so the one-sided intervals play a nice part because they give us an upper or a lower bound, right? And sometimes that's going to be useful. But these general asymmetric intervals are not typically going to be super useful because they're going to just be wider intervals in general, right? To get the same 1 minus alpha coverage, we're going to still need them to be even wider than they would otherwise need to be. And because of that, we're not going to typically use them. But it is important to make sure that you understand the definition of the confidence interval and recognize that any interval that has this property is going to be a valid confidence interval for the parameter we're thinking about. Okay, so intervals for the other piece to note here is that while this sort of asymmetric interval for the mean or for the proportion is not typically going to come up a lot, there are other intervals, such as those for the variance, that are asymmetric by default, right? So we're not always going to have symmetry in our intervals. And the key point to notice is that we never need symmetry in the intervals. It's just often if symmetry is available, that's going to be sort of the optimal thing to do. Okay, and so asymmetric intervals can be formed using a similar procedure to the symmetric intervals. They're typically going to be most useful if you take them to be the one-sided intervals, which will provide either an upper or a lower bound, but there's nothing stopping us. We can get as creative as we want when we're forming these intervals, and the key thing that we need to notice here is that as long as we have 1 minus alpha probability sort of contained under the curve, then it's going to be a valid confidence interval, right? And so however we want to distribute that is entirely up to us. It's just some choices are going to make more sense than others. With the one-sided intervals, we're going to get tighter upper or lower bounds. With the two-sided symmetric interval, then we're going to get sort of the most narrow. Every other asymmetric interval is going to be sort of less good in some way, but there's nothing stopping us from actually using those intervals if we ever needed to or had a reason to in practice.